Greetings, Math Club. With everything going on with the pandemic this semester, we've had to cancel most of our usual Math Club activities. The MAA conference was canceled. Probably not a great idea to bring a speaker to a campus at this point, and we can't have our usual end of the semester picnic. But we can still have an academic talk, and the topic that you picked based on the survey last week was how to add points at infinity to curves. So let's go ahead and take that question and frame it a little more precisely. The idea is, can we add a notion of a point or points at infinity for curves, which is compatible with the way that we usually find and represent points on curves in algebra? And by that we mean, in algebra we tend to think of points as defined by coordinates, and we think of a point as being on a curve if when you take its coordinates and plug it into the equation, it makes the equation true. It's important to frame things this way because different branches of math will often look at infinity in different ways. For example, we certainly can look at infinity in calculus. We tend to think of that as more of a direction, as x goes to minus infinity or x goes to plus infinity. It also describes a way in which a limit can fail to exist in a very particular way. If you go ahead and look at a graph, in this case it's the graph of y equals x over x minus 3, while you should probably never write down coordinates like this so your instructor will glare at you, they do make sense, sort of, in terms of the graph. As x goes out to infinity, the y value certainly heads to 1. X heads to minus infinity, the y value heads to 1. You creep up on 3 from the left, you head to minus infinity. Creep up on 3 from the right, you head to plus infinity. This works well in very limited circumstances. Basically, you have to be traveling directly to the left, right, or up or down. It wouldn't help if you were traveling in a path that had any kind of slant to it, so it's not great for what we'll need. You can also look at infinity in the branches of analysis and topology. A common way that they do that is through a technique called stereographic projection. So in stereographic projection, the idea is you lay the xy plane flat and you drop a sphere of radius 1 onto the plane in such a way so that the bottom of the sphere just barely touches the origin. Given any point in the plane, you can connect that to the top of the sphere with a line. That line will hit the sphere at exactly one other point, which kind of folds this point up onto the sphere. And as you move that point around the plane, that point will fold up to lots of different points on the sphere. Now, we can't actually do that in this picture, but if you allow the plane to go all the way out to infinity in all directions, as you move that point around, it'll actually cover up every point on the sphere except for the one at the very top. So the regular plane would correspond to the sphere take away that top point, and so we tend to think of that top point as the point at infinity. This works very well in analysis and some basic topology, but it's not very good for looking at curves and equations. So while this does work in some branches of math, it doesn't really work for what we're going to need. Now, to go ahead and define how infinity will work for us in curves, we're going to need to do a little pre-work first. So to start that pre-work, let's let x be the set of triples of the form x, y, z, where not all three of those numbers are 0. So it's okay for some of them to be 0, just not all of them to be 0. We'll define an association or a link between these triples by saying that ABC is associated to x, y, z. If you can find a number lambda not equal to 0, with x is lambda times a, y is lambda times b, and z is lambda times c. That is that the triple xyz is a non-zero scaling of the triple ABC. Just look at some examples of this. The triple 1, 2, 3 is associated to the triple 10, 20, 30. That's because if you take 1, 2, 3 and multiply it by lambda equals 10, it scales up to 10, 20, 30. 3, negative 2, 7 will be linked to the triple negative 6, 4, and negative 14. If you take these numbers and multiply them by negative 2, you'll get negative 6, 4, and negative 14. Slightly uglier example, the triple pi, e, and root 2 is linked to the triple pi squared, pi, e, and pi root 2. Take these first coordinates here, multiply them by pi, you'll get exactly the second coordinates here. 3, 4, 1 is linked to the triple 1, 4/3, and 1/3. That's by using the scaling factor lambda equals 1/3. If you like, you're saying multiplying by 1/3 or dividing by 3. Likewise, the triple 3, 4, 1 is also associated to negative 3, negative 4, and negative 1 by using the scale factor lambda equals negative 1. And this is pretty important because the same triple is not linked to just one triple. It's going to be linked to a bunch of triples because you can take these coordinates and scale them up or down basically by whatever you want as long as that's not going to be a factor of 0. And last, and maybe least in a sense, the triple 607 is going to be linked to the triple 607. It'll be linked to itself. And that's because if you use a scale factor of 1, 607 just becomes 607. Now, it turns out that that association of those triples with each other via scaling has three nice properties. So the first property, every pair XYZ is going to be linked or associated to that pair XYZ again, just like in that last example. And that's because you can always scale by a factor of 1. Second property, every time you have an association of a triple XYZ to ABC, you're also going to have that association the other way around. ABC will have to be linked back to XYZ. And that's because when you scale up by a factor of lambda in one direction, you can scale back down by using a factor of 1 over lambda in the other direction. And last, if you have the pair of associations, ABC is linked to XYZ, and XYZ is linked to IJK, then you'll also have the association ABC, that first one, is linked to IJK, the last one. And that's because if the first association uses a scale factor of lambda, and the second one uses a scale factor of mu, then the composite scaling will use a factor of just lambda times mu. Just to look at some examples to make sure these all make sense, certainly the triple 1, 2, 3 is 1 times itself, and therefore 1, 2, 3 really is linked to 1, 2, 3. 1, 5, 10 is linked to 2, 10, 20 because 2, 10, 20 is twice 1, 5, 10. But if you took this and divided by 2, that would mean 1, 5, 10 is 1/2 of 2, 10, 20. And that means 2, 10, 20 is links back to the triple 1, 5, 10. And last, the triple 1, 2, 3 is linked to 10, 20, 30 because you can get that by a scale factor of 10. 10, 20, 30 is linked to negative 20, negative 40, negative 60, as negative 20, negative 40, and negative 60 is negative 2 times 10, 20, and 30. So if you put these together, negative 20, negative 40, and negative 60 was minus 2 times 10, 20, 30. That in turn was 10 times 1, 2, 3, and minus 2 times 10 is negative 20. So if you go from start to finish, negative 20, negative 40, negative 60 is negative 20, 1, 2, 3. It's a scale of 1, 2, 3. And therefore 1, 2, 3 is linked to the triple negative 20, negative 40, and negative 60. These three properties, which are formally called the reflexive, symmetric, and transitive properties, are what you normally need to define the notion of equality or an equal sign. An equal sign's got to have three properties. Everything should be considered equal to itself. If A is equal to B, then B should be equal to A. And if A is equal to B and B is equal to C, then A should also be equal to C. These are exactly the three properties that our association of triples have. So from now on, we will consider two of our not all zero triples to be considered the same or equal if one is a scale of the other, and we'll write that as the triple ABC is equal to XYZ. Formally, this is the congruent symbol, but using a different symbol than the standard equal signs lets us have the coordinates different in both parts. Now, just some examples to make sure that we have the idea down. The triple 3, 1, 4 should be considered the same as the triple negative 6, negative 2, and negative 8. That's a scale factor of negative 2. And both of those should be considered the same as the triple 3/4, 1/4, and 1. Going from the first to the last, that's you scale by a multiple of 1/4 or divide by 4. Likewise, the triple 1, 0, 0 is considered the same as 9, 0, 0. That's a scale factor of 9, which in turn is considered the same as pi 0, 0. Going from the start to the finish, that's a scale factor of pi. And 3, 4, 0 should be considered the same as 1, 4/3, 0, multiplying through by 1/3 or dividing by 3. Or we could say it's considered the same as multiplying by 1/4 or dividing by 4, the same as the triple 3/4, 1, and 0. Now, this equality of triples gets us where we need to go and lets us define the notion of what's called the projective plane. Now, that we define the projective plane, which uses the symbol P2, or more formally, the symbol P2 of R, if you want to emphasize you're using real numbers. We'll define that to be the set of all possible triples, A, B, and C, which are real numbers, and not all 3 or 0, using the notion of equality given by our new version of the equal sign. Now my claim is this set, even though it looks like triples, can be thought of as the regular plane R2 together with extra points at infinity. Now, how do we do that? Well, start with a triple xyz, where not all three numbers are 0. If that last coordinate z is not 0, then you can scale the triple down by a factor of z, or if you like, divide by z. In that case, you would get that the triple xyz is considered the same as x prime y prime 1. When you divide by z, that's going to fast that last coordinate to be 1, and it'll probably change the x value and the y value. As an example, if you have the order triple 3, 2, 5, last coordinate's not 0, you can divide by 5. We're going to consider that to be the same as 3/5, 2/5, and 1. In that form, x prime y prime 1, there's no way to scale this triple up or down any further without destroying the 1 in the last coordinate. So we tend to think of this as sort of the standard form for the type of triple where the last part's not 0. Also, a point in the regular plane, like the point 3, 2, can be brought into the projective plane just by tacking 1 at the end. So the point 3, 2 becomes the triple 3, 2, 1. And likewise, a triple in P2, which has a 1 at the end, like the triple 9, 7, 1, can be sort of brought back down into the regular plane by dropping that 1, in this case to get the point 9, 7. And so at least for now, we're going to consider points x, y, z, where z is not 0, to be the regular points or the normal points from R2. Now, what if z is 0? Well, if z is 0, then the triple itself is going to look like x, y, and 0. And because we're not allowed to have an all-0 triple, that means not both x and y can be 0. Kind of breaking this into cases, if z is equal to 0 but x is not, then we could take that triple and scale it down by a factor of x, or if you like, divide through by x, to get a form for the point which, starting with x, y, 0, drops down to 1, y prime, and 0. Dividing by x can't change the 0, but probably changes the number in the middle. For example, the point 2, negative 7, 0, dividing by 2 becomes the point 1, negative 7, 0, or negative 7 halves and 0. You can't scale this type of triple up or down without destroying that 1 in the first coordinate, so this becomes sort of the standard form for this kind of triple. We're going to consider all of these points to be out at infinity, and is actually going to give us an infinite number of such points because you can put any number y prime you want in the middle, and there's an infinite number of such choices. Now, the last option is if z is 0 and x is 0, then the triple you started with really looks like 0, y0, where y is not 0. Scaling this triple down by a factor of y gives you the point 0, 1, 0, and there's no way to scale this up or down without destroying that 1 right there in the middle. So this is sort of the standard form for this kind of point. This one point is also considered to be out there at infinity. So in summary, when you have z not equal to 0, that means you've got a point in the regular plane. You scale that point to get a 1 in the last spot, and that will let you figure out which point you have. And z equals 0 means you are at a point out at infinity. Now, in terms of some examples, the triple 3, 5, 4 corresponds to a point in the regular plane, because we know that last coordinate z is not 0. Dividing through by that 4 gives the point 3, 5, 4 is considered the same as 3/4, 5/4, and 1. And that means that point 3, 5, 4, whichever name or set of coordinates you want to use for it, will correspond to the point just 3/4 and 5/4 in the regular plane. If we're handed the triple 0, 7, 0, we know that's a point out at infinity because we know the z value is 0. As we can't scale it using the first coordinate, we'll have to scale it using the second. So dividing through by 7 or scaling down by a factor of 7 changes that triple to the triple 0, 1, 0, which is the standard way to write that kind of specific point out at infinity. Finally, if you have the triple 4, 1, 0, that's also a point out at infinity because the z value is 0. As the first coordinate is not 0, we can use that for scaling. So multiplying by 1/4 or dividing by 4 tells us that the triple 4, 1, 0 is considered the same as 1, 1/4, 0. And that's the standard way to write this kind of point that's out at infinity. It turns out that the move from R2 to the projective plane causes a problem for how we define points being on a curve. When we go from R2 to the projective plane, We do that by adding a third coordinate to the points, as well as the notion of scaling the triples but keeping the point the same. It turns out that this scaling can cause a major issue for the way we normally test to see if points are included in the graph of an equation or not. So as an example, let's just consider the basic curve y equals x squared in R2, everybody's favorite parabola. We know the point 2, 4 is on the curve because when you take the coordinates and plug them into y equals x squared, 4 really is 2 squared, so that point is considered on the curve. When we transfer 2, 4 into the projective plane, we do that by tacking the 1 on the end, so it becomes the triple 2, 4, 1. Now, if we use the triple 2, 4, 1, the coordinates will still satisfy y is x squared, because 4 really is still 2 squared. But the point 2, 4, 1 is also the same as the point 6, 12, 3, and if you look at the coordinates of 6, 12, 3, they do definitely not work in y equals x squared. 12 is definitely not the same as 6 squared. The fact that we can scale coordinates and not change the point that we're talking about is not really compatible with the idea of being a solution to y equals x squared, and this is a big problem. Now, it turns out there is a way to fix this problem, but to do that, we need to change not just the point when we bring it into the projective plane, but the equation as well. In a sense, the core of the problem is that for the original equation y equals x squared, when you scale x and y by the same amount, it works differently on the two sides of the equation. The left-hand side, which is just y, gets scaled once, but the right-hand side, which is x squared or x times x, gets scaled twice, and this breaks the equality between the two values. One way to fix the problem is to add the new and currently missing variable z to the equation in a manner that makes all the parts of the equation scale exactly the same way. And when you do that, you're now going to talk about what's called homogeneous polynomials and equations. So a polynomial in however many variables you want is called homogeneous if all of the terms in it have the same total degree. So the total power on each term is the same. Likewise, we'll say that a polynomial equation is considered homogeneous if all of the terms on both sides have the same total degree. Now, just as some examples, if we look at the polynomial x minus xy plus y cubed, it is not homogeneous. The terms do not have the same total degree. We have 1 power here, a total of 2 powers there, 1 for x, 1 for y, and 3 powers here. So this is not homogeneous. The polynomial x squared plus y squared minus xz plus z squared is homogeneous. If you look at the terms, that's power 2, total power 2 between them, and power 2. This counts as homogeneous. As an equation, y equals x squared is not homogeneous. The left-hand side, you only have a total degree of 1. The right-hand side, you have a total degree of 2. The more complicated equation, xy squared plus yz squared plus z cubed equals 0 does count as homogeneous. All the terms on the left-hand side have a total degree of 3, and the right-hand side, which is 0, doesn't really have terms in the usual sense, so it kind of satisfies this trivially. Or if you like, the total degree of 0 is just undefined. Now, most of the equations that we do want to work with are not going to be homogeneous when you take them from the regular plane, so we need to introduce a process which is called homogenization. Now, if f of xy is a polynomial in x and y, and that polynomial has total degree t, total degree d, then the homogenization of that polynomial, it's given by a technical formula. It's not uncommon to use f hat or f bar to represent the homogenization, but it is a polynomial in 3 variables x, y, and z, and the formal definition is it is z to that total degree times f of the fraction x over z and y over z. This formula works really well as a definition and it actually has some nice theoretical properties, but it's probably not the easiest way to do it in practice. Another way to find this homogenization, you can find it more easily by adding just enough powers of z to each of the terms in f of xy to make all of the terms have the same total degree d. When you do that, you will create a homogeneous polynomial. That's for a single polynomial. The homogenization of a polynomial equation of total degree d, you find by adding enough powers of z to each term on both sides to bring all terms to that same total degree d. Now, just some examples of this. If we start with x minus y squared plus xy cubed, that's degree 1, degree 2, degree 4. So you want to add enough powers of z to each term to bring them up to total degree 4. Well, we're missing 3 here, 2 here, and none here. So we'll homogenize that as xz cubed, because that now has degree 4, minus y squared z squared, that has degree 4, and then xy cubed, that has degree 4. So this polynomial is now homogeneous, and that's the homogenization of the polynomial here. Likewise, if you look at x squared minus y squared plus 5, that's not homogeneous. That's degree 2, degree 2, degree 0. We want to bring all the terms up to degree 2. The x squared is okay, the y squared is okay, we're missing some on the 5. So the homogenization of this polynomial would be x squared minus y squared plus 5z squared. Just looking at an equation or two, the homogenization of the equation y equals 2x minus 3, that's degree 1, degree 1, degree 0, so you want to bring everything up to degree 1. We would do that as y is 2x minus 3z. The y was already at the right power, the 2x was already at the right power, we just needed to fix that last bit. Likewise, if you have the equation x cubed minus y squared is equal to x, and you want to homogenize it, that's degree 3, degree 2, degree 1. We've got to bring it all up to degree 3. The first term was already okay. We'll make that minus y squared z to get that up to degree 3 is equal to xz squared. As a final example, the homogenization of x to the 5th minus xy to the 4th plus 2y to the 5th, that's total degree 5, total degree 5, total degree 5. Well, we'd have to bring this up to total degree 5, and well, that's pretty much done. It's already, each term already has total degree 5. And that's one nice bit about the homogenization process, is if what you started with was homogeneous to start, which this is, then the process of homogenization does not change anything. It's also worth mentioning that this process can be reversed. In other words, if you start with a regular polynomial and then homogenize it, you can reverse the process by simply plugging in z equals 1. So as an example, if you start with x minus y squared plus 2x cubed, the total degree here is 3, so we're missing 2, missing 1, not missing any. The homogenization would be xz squared minus y squared z plus 2x cubed. If you take the homogenization and you plug in z equals 1, well, that becomes x for the first term, just minus y squared for the second term, and then plus 2x cubed for the last term, and you're back exactly where you started. If you have an equation like x squared minus y is equal to 5, that's degree 2, degree 1, degree 0. We would homogenize this as x squared minus yz is equal to 5z squared. If we take this and replace z with 1, it drops back to x squared minus y is equal to 5. And that's exactly where the equation that we started with. So you can homogenize things, bring it up to x, y, and z, and once it's homogeneous, you can bring it back down just by using z equals 1. This probably isn't terribly shocking that z equals 1 is important here. Remember, when you have a point that's not at infinity, it's going to be represented by a triple where you can set that last coordinate equal to 1. Now, how does homogenization fix our problem? Well, the answer is given by the following theorem. Let E be an equation in x and y, and we'll let E hat be its homogenization in x, y, and z. Then two things have to be true. First, if the coordinates of a triple work in E hat, then so do the coordinates of any non-zero scaling of t. They'll work as well. That is, being a solution to the equation E hat in P2 is compatible with scaling. When you scale a solution, it still works, and that means being a solution is well defined. Second, the solutions x, y, z to the homogenization E hat come in two forms. Solutions of the form AB1, where the ordered pair AB is a solution to the original equation E in the regular plane, together with maybe some points at infinity, where z will be 0. This basically tells you that when you move an equation from the regular plane to the projective plane via homogenization, you're going to keep all the regular points you started with, adding a last coordinate of z equals 1 to them, and maybe get some new points that are considered to be at infinity, where z is 0. And that's exactly what we wanted to do. The set of solutions to E hat in the projective plane is called the projective completion of the solutions to E. It's called a completion because it contains all the old solutions, or at least a version of them, together with some potential new solutions as well. Now, just as an example of how this works, let's go back to the equation y equals x squared, the parabola and the plane. The homogenization of this is going to be the new equation yz equals x squared. That has total degree 2. We've now brought all the terms up to degree 2. We know that 2, 4 is a point on the parabola y equals x squared on the regular plane. When we bring 2, 4 into the projective plane, we do so as the triple 2, 4, 1. That is guaranteed to work in the equation yz is x squared. Just as a quick check, 4 times 1 really is 2 squared. Even better, any scaling of that point is going to have to look like 2 lambda, 4 lambda, and lambda, multiplying through by lambda. And if you set the x coordinate to 2 lambda, the y coordinate to 4 lambda, and z is regular lambda, take those, plug them into yz equals x squared. You'll start with yz is x squared. Well, 4 lambda times lambda, that's y times z, is that really the same as 2 lambda all squared? Well, that's 4 lambda squared on the left, 4 lambda squared on the right. Congratulations, the order triple 2 lambda, 4 lambda, lambda does work in the projective equation yz is x squared. And that means that this homogenization, yz equals x squared, works well with scaling, in the sense that when you scale a solution, the new triple you get is guaranteed to be a solution. Now, all the points x, y on that normal graph of the parabola come into the projective plane as the points x, y, 1, but what about points that are out at infinity? Those points are defined by the last coordinate being 0. If we take the homogenization, yz is x squared, and use z equals 0, it's going to become x squared equals 0, or just plain x equals 0. That means a point at infinity on the parabola would be xyz. That's 0, y0. Z was 0, and we now know x is 0. Scaling that down to standard form, that becomes the point 0, 1, 0. And that's going to be a point at infinity for this curve. And in some sense, it's actually considered a double point, because when you look at the equation x equals 0 that came up, 0 is a solution to that with multiplicity 2. So the projective completion of the graph of y equals x squared consists of all the regular points, or regular solutions, together with the doubled point 0, 1, 0 out at infinity. Now let's take a look at some other examples of moving curves into the projective plane. And let's start with the line y equals 2x minus 5. If we want to bring the line y equals 2x minus 5 into the projective plane, you need to homogenize it first. The homogenization is pretty straightforward. That's just going to be y is 2x minus 5z. All of the normal points in the plane, which would look like x and 2x minus 5, are going to count as part of that projective completion, and they'll come in as the triples x, 2x minus 5, and 1. You just attach the 1 at the end. To see if that line is going to hit infinity anywhere, we let z equal 0. This turns the homogenization into simply the equation y equals 2x. So the points at infinity have the form starting with x, y, z. We knew that z was 0 and y was 2x. Here the x can't be 0 because you're not allowed to have all three be 0. Scaling this down by a factor of x changes that to the point 1, 2, 0. So the line y equals 2x minus 5 hits infinity out at a single point, and the projective completion of y is 2x minus 5 is all of the regular points on the line together with that infinity point 1, 2, and 0. Now next, we'll generalize this a little bit and take a look at the line y equals 2x plus b. So the equation y equals 2x plus b, where b is any constant, doesn't represent one line of slope 2, it represents all lines of slope 2. To bring it into the projective plane, we homogenize it to get the equation y equals 2x plus bz. All terms here have degree 1. The projective solutions to this include all of the regular points on the line. To find the points at infinity, again, we're going to set z equal to 0, which takes this equation, and with z equals 0, reduces it to y equals 2x. This gives us the projective point. We started with x, y, z. We knew z was 0. We know y is 2x. And scaling down by x gives us that point 1, 2, 0 again. So all lines of slope 2 are going to hit infinity at the exact same spot. They're going to hit it at the point 1, 2, 0. This is not a coincidence. In general, when you look at the projective completion of all lines of the form y equals mx plus b, you can run through the same process. and it turns out they all hit infinity at the point 1, m, 0. Likewise, if you look at the equations of vertical lines, x equals a, they will all hit the point at infinity 0, 1, 0. And what this tells you is there are no parallel lines in the projective plane. Lines that are parallel in the normal plane will actually cross at a single point at infinity that corresponds to their slope if the line is not vertical, or the lack thereof if it is vertical. As another example of bringing a curve into the projective plane, let's take a look at the unit circle x squared plus y squared is 1. To bring that into the projective plane, we have to homogenize that. That's degree 2, degree 2, degree 0, so that's going to become x squared plus y squared is z squared. The projective completion will include all the regular points on the circle, which, if you were being clever and using trigonometry, would be points of the form cosine theta and sine theta, and then bring them in as triples of the form cosine theta, sine theta, and 1. To see what happens at infinity, we take x squared plus y squared equals z squared and let z be 0. That's going to change the equation to x squared plus y squared is 0. Since x and y are real, though, x squared and y squared individually must be 0 or bigger, so therefore x squared plus y squared equals 0 can only happen when both x and y are 0. If x and y were 0 together with z equals 0, that would lead to the all 0 triple, which is not allowed, and therefore the projective completion of the unit circle doesn't have any points at infinity. All of its points are just going to be the regular points on the unit circle. Another example, let's take a look at the curve y squared is x cubed minus 3x. This is an example of a type of curve known as an elliptic curve, which has lots of applications. This has total degree 3, so when we bring it into the projective plane and homogenize it, we need to get every term up to degree 3. So the homogenization will be y squared z is x cubed minus 3xz squared. That's going to contain all of the regular points from y squared is x cubed minus 3x, together with maybe some points at infinity. To check for the points at infinity, we set z equals 0. That's going to change the homogenization to, well, that's going to be a 0, that's going to be a 0. That becomes x cubed equals 0. And the only solution to that is x is 0, and that actually happens as a triple root. So that means the projective completion only contains one point at infinity. We knew x is 0, we know z is 0, so y could be anything. Scaling down by y, that gets a 0, 1, 0 as a triple point. The triple nature of this point actually corresponds to being an inflection point on the curve at that point out at infinity. As the last example of bringing a curve into the projective plane, let's take a look at the hyperbola y squared minus x squared is 16. To bring that into the projective plane, we homogenize it as y squared minus x squared is 16z squared. That's going to include all the regular points on the hyperbola. The points at infinity would be where z is 0. That's going to change the equation y squared minus x squared is 16z squared into y squared minus x squared is 0, or y squared is equal to x squared. Taking square roots on both sides gives us the absolute value of y is the same as the absolute value of x, or if you like, y is plus or minus x. So the points at infinity for this hyperbola are going to be of the form x, x0, which if you scale it down by a factor of x gives you 1, 1, 0. And taking the minus sign, that gets you x minus x0, which scales down to the point 1 minus 1, 0. And in the projective plane, the hyperbola hits infinity at exactly 2 points. Now, it turns out there's something neat about this, which actually solves a problem in one of our other textbooks. These points actually shed some light on something that happens with the hyperbola. In our analytic geometry text, there's a problem to find all of the lines through 3, 3, which are tangent to y squared minus x squared is 16. If you go through the process of finding the tangent slopes, which is fairly easy if you use calculus and it's a little bit harder if you use pure algebra, you'll find that there are 2 tangent slopes. M is 1 and negative 7/25, and therefore 2 tangent lines. You have the slopes, you know they go through 3, 3. You can get the equations of the lines pretty easily. The first one for m equals 1 gives you y equals x, and the second one gives you y is minus 7/25 x plus 96/25. But if you graph these 2 lines together with the hyperbola, something a little weird happens. The graph looks like this. Here's the line with slope negative 7x over 25. Here's the point 3, 3. And you can find that this really is a tangent line. It's tangent to the hyperbola right over here. However, if you look at the line y equals x, it doesn't hit the hyperbola at all. It's actually one of the asymptotes to the hyperbola. But that y equals x line is supposed to be tangent to the hyperbola somewhere. And this is a big problem in the analytic geometry text. There's no real good answer for it. However, if you bring these into the projective plane, it fixes the problem. It turns out both the hyperbola and the line y equals x hit infinity at the same spot, which is the point 1, 1, 0. And so the line y equals x turns out to be tangent to the hyperbola out at infinity. So y equals x really is a tangent line in the projective plane, just not at one of the normal points. It's tangent to the hyperbola at a point out at infinity. Now that we have a good idea of how to take regular curves and bring them into the projective plane, we can kind of tweak this idea a little bit, and something interesting shows up when you try to change how you're going to track points at infinity. Now, in the projective triples x, y, z, we've been associating z equals 0 with points out at infinity, and points z not equal to 0, which after scaling is really z equals 1, with regular points in the plane. This is because we started out with regular points x, y, and then introduced the variable z at the end. But if you were to start with triples x, y, z and not get them as the end result of a process, those triples wouldn't inherently know that z is supposed to be encoding this normal versus infinity information as 0 or not 0. That's an interpretation that we place on that last variable z. Maybe points at infinity could be tracked by x, maybe they could be tracked by y, or maybe even by a combination of those variables like x plus y plus z. And some strange things can happen when you shift the notion of how you're going to track infinity. So as an example of the effects this can have, let's go back to the unit circle x squared plus y squared is 1. When you bring this into the projective plane, it becomes x squared plus y squared is z squared. And if you wanted to bring this back down to the regular unit circle, you can recover the normal part of that completion by putting z is equal to 1. Remember that dehomogenizes it, takes the z out. But what after bringing it up to the projective plane, you forgot that z was to control infinity, and instead decided that y was going to control infinity? Then you would recover the normal plane part of the curve by using y equals 1 instead of z equals 1. If you put y equals 1, you'll get x squared plus 1 is z squared, or z squared minus x squared is 1. And that's not a circle, that's actually a hyperbola. So by bringing the circle up to the projective plane one way and bringing it back down in a different way, it actually transforms the unit circle into a hyperbola. Something similar happens if you start with the hyperbola or the parabola, y equals x squared. We can bring this into the projective plane in the usual way now to become yz is x squared. If we were, instead of thinking of z as controlling infinity, if we bring it back down to the regular plane by thinking of x as encoding infinity, we would do that by saying x equal 1. That turns this equation into yz equals 1, which is also a hyperbola. It's a hyperbola which is rotated at 45 degrees to the coordinate axes. So going up to the projective plane one way, but back down in another, transforms that curve from a parabola to a hyperbola. In fact, if you take any conic section, either the ellipse and circle, parabola, and hyperbola, it turns out given any one of these three, you can flip it to any other of the types by bringing the curve up to the projective plane one way and bringing it back down in another specific way to get the type that you want. And that unifies those very different looking conic sections into just one type of curve. And that's a nice application of shifting the idea of what you think controls infinity. So in summary, why should we use the projective plane? Well, first, and this is where it really comes from, is it adds the notion of curve points out at infinity in a fairly consistent and relatively easy to find way. Another nice feature is that it removes the notion of parallel lines, because previously parallel lines cross out at infinity, and that puts all line pairs on the same basic footing, and it removes the need to consider special cases in some geometry problems where lines could be parallel. A really good example of that is Pascal's mystic hexagon theorem. This is a picture of what the theorem might look like here. Pascal's mystic hexagon theorem says that 6 points lie on the same conic if and only if some geometric condition holds. Whenever you have 6 points, you can draw a hexagon through those points. The hexagon will have 3 pairs of opposite sides. In this case, we've got a green pair, a red pair, and a blue pair. You can extend those sides. Sometimes they meet inside the hexagon, sometimes they meet outside the hexagon. And Pascal's mystic hexagon theorem says that these 6 points lie on the same conic only if these 3 points actually lie on the same line, if they're collinear. And this gives you a nice kind of geometric test for whether points are conconic or not. Now, if you try to look at this straight away, there are lots of special cases to this. In particular, if I shift these points around, these green lines may move from non-parallel to being parallel, which means this third point disappears, and that becomes a special case. You often handle this in geometry by saying, well, if I just move the points a little bit, that would no longer be the case. But you don't have to wave your hands quite so hard if you're using the projective plane, because even if the opposite sides here are parallel, then this point will still exist. It exists out at infinity in a nice quantifiable way, and you can still check that these 3 points are collinear. Another nice feature of the projective plane, the addition of points out at infinity, can sometimes give you a good explanation of why certain points or tangent lines are missing geometrically when they make good sense in algebra. That was our example of the tangent line to the hyperbola y squared minus x squared was 16. In many cases, those missing points or tangent lines actually do exist. They're just at specific points at infinity that you would not include in the regular graph. Another feature is sometimes changing how you track or interpret the points at infinity can unify very different looking curve types like the conic sections. You can flip circles into parabolas, parabolas into hyperbolas, and so on. And the third one, which we didn't really discuss, there's a really nice theorem called Bezout's theorem, which says if you let your projective points use complex number coordinates, which you would denote by P2 of the complex numbers instead of P2 of the reals, you treat everything else the same way, you link pairs if they scale by complex numbers instead of just real numbers, then a curve C1 of degree A and a curve C2 of degree B that only have a finite number of intersection points will have exactly A times B of them as long as you count multiplicity and you also count points that happen out at infinity. So for example, lines have degree 1, so a line crosses another line at 1 times 1 or 1 point in P2 of C. Likewise, if you have two conics, that's degree 2 and degree 2, those two conics would cross 4 times. A line and a conic would cross 1 times 2 times. A conic and a cubic would cross 2 times 3 or 6 times, and so on. And this is a really useful theorem. It shows up a lot in geometry and in a lot of problems that kind of border between the realms of algebra and geometry. And in fact, this is often one of the first big theorems that you see in a branch of math called algebraic geometry. So that is the end of the talk. I hope you enjoyed it. If you have any comments or questions, you can reach me by email or post in the YouTube thread below. So hope everyone is having a good semester, hopefully with everything going on a safe semester. And if I don't see you over the summer, hopefully I'll be seeing you in person this fall.